Welcome back. So far we've talked about how to calculate determinants of small matrices 1 by 1 and 2 by 2, and then how to calculate minors and cofactors, which are related to submatrices. Now we're going to put those pieces together and learn how to calculate the determinant of a large matrix. Well, not too large. We'll start the next size up. We'll go to a 3 by 3. If we wanted to calculate minors and cofactors of larger matrices than we just did, like we just did an example with a 3 by 3, it was possible to find the minors and cofactors of a 3 by 3 matrix because the determinant part of the calculation requires us to take the determinant of a 2 by 2, and we know how to do that. But if we were asked to find the minors and cofactors of a 4 by 4 matrix, then part of that calculation would be taking the determinant of a corresponding 3 by 3 submatrix. Now we don't know how to do that. It turns out that we can calculate the determinant of a 3 by 3 matrix by expressing that determinant in terms of cofactors. For 5 by 5, we would need determinants of 4 by 4 submatrices. Each such calculation would in turn require determinants of 3 by 3 submatrices. We'll see that those required calculations themselves of 2 by 2 sub-matrices, and it would go on forever. It would keep going on and on as the matrix gets larger. We would have these nested submatrix calculations with nested determinant calculations inside them. So the process I'm going to show you is a very computer sciencey type of process. It's an algorithmic approach. It's the way that you would code it if you're telling a computer to do a determinant, but it's not necessarily the smartest way to do a determinant. It can be very, very slow, inefficient, and it doesn't take into account all the shortcuts that are available when calculating determinants. And we'll learn what those shortcuts are later. So I guess you could call this is the dumb way of doing determinants. If you're a computer, and computers, believe it or not, are epically stupid. We are at no risk of being taken over by AI anytime soon. What we'll do is when calculating a determinant, we'll do what's called a row expansion. We'll pick the first row to begin with to do an expansion along, and then we'll see that it doesn't matter what row we use, and indeed it doesn't even matter if we use a row or a column to do the expansion. Then we'll look at other tricks. We'll look at, can we look at the structure of the matrix and tell right away what the answer is? Maybe sometimes we can tell immediately that the determinant is 0 just by looking at the matrix. Or we can maybe do some manipulations related to row reduction. And then after doing those manipulations, some shortcuts will be revealed. So there's quite a journey through the process of calculating determinants. Again, I warned you once, it's going to look scary. There's going to be notation that is frightening, but we will replace that notation with better methods, more friendly methods. Okay, here we go. If you're looking at a square matrix A that's 3 by 3 or larger, so 3 by 3, 4 by 4, 5 by 5, then how you would calculate the determinant, here's one way. Okay, there's one way of an infinite number of ways to calculate the determinant of that matrix. You can calculate the determinant as the entry in the first row, first column, so A11 multiplied by cofactor C11 plus one entry over to the right, A12 multiplied by cofactor C12 plus the next entry to the right of that, A13 times cofactor C13. And you keep doing that until you finish off that row, until you have each element of that first row multiplied by the corresponding cofactor that pairs up with that element. You add up all those pieces, and that's going to be the determinant of the matrix. That means if we're looking at a 3 by 3 matrix, we're going to need to calculate 3 2 by 2 determinants. this might be the first place that you see this notation, this so-called summation notation. This is a special math symbol. It's a capital sigma. It means sum, and sum just means add. And it's a fancy expression for adding up a bunch of stuff. The anatomy of this expression is as follows. J equals 1 down on the bottom. J is a counter. J is just keeping track of which element are we at. J equals 1 means we're adding the first one. J equals 2 means we're adding the second one, and so on. N tells us when do we stop counting? Count up to how many things. So we're starting from the first thing and adding at the nth thing. If n is 10, then we're adding up 10 elements, or whatever's inside there. And then there's something, we would have something in here that we're actually adding up. We could rewrite this expression at the top here. Determinant of A is equal to A11, C11 plus A12, C12 all the way up to A1n, C1n. We could rewrite that as the sum from J equals 1 to n. So J is controlling which column we're in. We're always in row 1. So the first entry in top left is row 1, column 1. We go to the right, now we're in row 1, column 2, and so on. So J is just counting what column we're currently working on. The first term of that sum is A11, multiplied by negative 1 to the power of 1 plus 1, multiplied by the determinant of A11. So this piece in here, this negative 1 to the I plus j times the determinant of Aij, that is C1j. The cofactor the cofactor at row 1, column j. So you have the entry at row 1, column j multiplied by the cofactor at row 1, column j. I'm going to put in a video that's optional after all this stuff on determinants about this summation notation and dig a little bit more into it. It's important for finance, it's important for statistics and econometrics and some other subjects. And those, I'll label it very clearly. Those videos are optional. They're not part of Math 1229. You won't be tested on them. I'm just going to proceed with course material right now and then append those videos at the end. Okay. So let's use that strategy to find the determinant of this matrix. So step 1 is to know the formula, the determinant. The determinant of the matrix, determinant of A, is going to be A11 times C11 plus A12 times C12 plus A13 times C13. So I'm going to put in the corresponding numbers. A11 is 1 times C11 plus A12 is 2 times C12. And we have plus A13 is 3 times C13. Now I'm going to calculate those submatrices off to the side. A11, the submatrix A11, we delete row 1, column 1. So I'm just going to write the whole thing 1, 2, 3, 2, 1, 3, 3, 2, 1. So we delete row 1, delete column 1. We get 1, 3, 2, 1. So C11 is negative 1 to the power of 1 plus 1 times the determinant of A11. So negative 1 squared times 1 minus 6. We do the down product minus the up product. 1 times 1 minus 2 times 3. We get positive 1 times negative 5, which is negative 5. So that'll go here for C11. Now we'll calculate the next one. The next, we need C12. That means we have to construct the submatrix A12. So 1, 2, 3, 2, 1, 3, 3, 2, 1. Just copying the matrix. I'm going to delete row 1, column 2, and the surviving terms 2, 3, 3, 1. Then C12 is -1 to the 1 plus 2 times the determinant of A12. So -1 to the 3 times the determinant A12. We do dot products minus dot products. 2 times 1, 2, minus 3 times 3, 9. So we get -1 multiplied by -7, which is +7. I'll put that one here. And then the last cofactor calculation, we're going to need the submatrix A13. So A13 is 1, 2, 3, 2, 1, 3, 3, 2, 1. Move the first row, move the third column, and we have the submatrix 2, 1, 3, 2. Now our cofactor C13 is equal to -1 to the 1 plus 3 multiplied by the determinant of that new submatrix we just found, A13. So -1 to the power 4 times down product 2 times 2, 4, minus up product 3 times 1, 3. -1 to the power 4 is 1, so we have 1 times 1, which is just 1. So I'll put a 1 there. So we have 1 times -5 plus 2 times 7 plus 3 times 1. So -5 plus 14 plus 3. We get 12 for the value of the determinant. So it's quite a bit of work to calculate the determinant of a 3 by 3 matrix using this submatrix formalism. I'll show you a shortcut though. Be sure I got the right answer. Yeah, okay. This is called the secret method. The secret method is not secret. It's in the textbook. It's in one of the homework problems. But it's not in the main part of the book. So it's kind of secret. I haven't done it for a while, so I might mess it up. The way it works is you make 2 copies of the matrix, side by side. 1, 2, 3, 2, 1, 3, 3, 2, 1. 1, 2, 3, 2, 1, 3, 3, 2, 1. And then your determinant is equal to the down products minus the up products. So here's the down products. The first down product is 1 times 1 times 1, which is 1. The second down product is 2 times 3 times 3. So 2 times 3, 6 times 3 again, 18. And the third and last down product is 3 times 2 times 2. So plus 12. And then minus the up products. So 3 times 1 times 3 is 9. 2 times 3 times 1 is 6. And 1 times 2 times 2 is 4. and we simplify. So this is 31 here minus 19, which is 12, which is the same answer. You could show that all the multiplications that happened here also happen here. So for example, we have hold on. Twelve, 1, 4. Oh, I guess not. Never mind. Oh, of course not, because you can pick any row, any column. Never mind. No, you can't show that. But you can show that this method is always going to give you the same outcome as the cofactor calculation. Different intermediate steps, but same final answer. This should remind you of one of the methods for calculating cross products. And indeed, you can go back and redefine the cross product as a type of determinant. All right, what about a 4x4 matrix? Now in the following, I don't want you to don't add this to your notes, okay? Don't write this down. It's a waste of time to write this down because you're not going to calculate any determinants using the method I'm about to show you. This is just like an amusement park ride. You sit back and you just don't take notes, okay? The determinant of this 4x4 matrix would be calculated as a sum of entry multiplied by a cofactor. And we're going to have 4 of those. The first entry, top left entry, multiplied by the top left C11 cofactor, plus the entry row 1, column 2, multiplied by cofactor C12. And then the same for the third and the same for the fourth. Each of those cofactor calculations is -1 to the I plus j, so -1 to the row number plus column number, times the determinant of the submatrix Aij. So there's your -1 to the I plus j's with I plus j simplified, and your submatrices. We started with a 4x4, so the submatrices are 3x3. Now, we could use a secret method to calculate the determinant of each of those 3x3 matrices. We're supposed to pretend we don't know that. So what we would do is we would use cofactor expansion. We would expand the determinant of the 3x3 into a bunch of 2x2 determinants using that same cofactor method. So what's happened from that step to this step is that the constants in front of the determinants have been simplified. Okay, and then the determinant of the matrix is highlighted in yellow. That's shown there in its cofactor expansion, 3 times the determinant of the submatrix A11 for that new matrix A, and so on. Down it goes for the other pieces as well. And there's all the multiplications. There's your final answer, and it's horrible. The odds of getting all this right using this approach, it's almost 0. You're guaranteed to make an error somewhere along the chain. Now, computers, despite being incredibly stupid, are able to do this without making mistakes because it's mechanical. The computer doesn't have to think. It'll just do exactly what it's told, and it won't make the types of errors that human beings make. But it also won't be creative, and it won't solve it in any type of efficient way. It'll do this. Now, each one of those steps isn't that bad. It's systematic. You could break it down. If you had lots of time, lots of paper, lots of patience, you could do it. And there's ways of checking your work. Notice that some of those steps weren't necessary, so we can go back and look at let's see. This calculation here. I have a 0 up here. Why on earth would I calculate this determinant? Because it doesn't matter what's there. Some number is going to come out of that. I'm multiplying it by 0. It's just going to disappear. And there's a whole bunch of those. So what we could have done, there. What we could have done is identified that ahead of time. Identify that there's a bunch of zeros hanging around. And said all those determinants don't need to be calculated. Like just zero them out. Like who cares what they are? Like who cares if it's 0 times 7 versus 0 times 3? It's still 0. Now I only have 3 2x2 determinants to calculate. So it's a little better. Okay, so there it is. We focused only on the pieces that survived, and the calculation is still horrible. What we can do instead is use the fact that this determinant operation, the definition I showed you, isn't complete. The definition I showed you said that you have to expand along row 1, and the truth is you can pick any row that you want, or any column. So for example, we could expand along row 2. We would have 0 multiplied by cofactor C21 plus 3 multiplied by cofactor C22 plus 0 multiplied by cofactor C23 plus 0 multiplied by cofactor C24. And all those are going to disappear except the second one, except 3 times cofactor C23. So we would only have a single 3x3 determinant to calculate. We could also expand along column 1. You would get 1 multiplied by cofactor C11 plus 0 multiplied by cofactor C21 plus 0 multiplied by cofactor C31 plus 0 multiplied by cofactor C41. And believe it or not, both of those calculations are going to output the same determinant that we saw already. So to show you what happens if we pick the second row, we would have 0 multiplied by that cofactor plus 3 multiplied by the cofactor C12 . 3 times C22, 0 times C23, and 0 times C24. So all those pieces are multiplied by 0. Don't calculate those determinants. We just have 3 multiplied by the determinant of that 3x3 matrix, which I would use a secret method on that. Down products minus up products and get the answer fairly quickly. Or you could expand along column 1 of that matrix, do cofactor expansion, which is arguably faster, but I think less straightforward. I just do the secret method. And there you get your answer, you get your 48, same as before. So, this isn't the shortcut still. Like, this is still not the smartest way to do things. We're going to learn a better way than this. But it's much better than that first calculation that had like just the first row and 4 3x3 determinants to calculate. If you're curious, if you want to try it on your own, go back and redo this calculation by starting with the expansion along column 1. Use the secret method if you want for the resulting 3x3 matrix in your cofactor calculation, and make sure you get 48. And if you really want to do an experiment, pick the third column, or pick the third row, or pick some other row or some other column, and check that the cofactor expansion matches. Because I don't prove that the determinant is not sensitive to the selection of the row or column that you expand along. That proof is not part of the course. It isn't that it's impossible, it's just that it would turn you off on this more than you're already turned off on this. And we'll continue in the next video.